A very good evening to all of you. So today I'll be telling you more about three-phase induction motor. These three-phase induction motor are most commonly used in the industries. So if you go to any industries, you will find the wide variety of applications as the induction motor drives. So basically, this induction motor are of two important type. The first one is the squirrel cage induction motor, and the second one is the slip ring, or you can say a wound rotor induction motor. Normally, in the slip ring induction motor, we can connect the external rotor resistance with the help of slip rings. So by adding a rotor resistance, what you are doing, you are just having the speed control. So you can have the speed control by the rotor resistance only in case of the slip ring induction motor. So I won't be going in that much detail. I'll be telling you some formulas, and based on the formula, we'll try to solve some numericals. So basically, this in induction motor there are three important parts. The first one is the stator, the second one is the air gap, and third one is the rotor. So induction motor is an AC motor, so which is going to convert the three-phase electrical power into the mechanical power. Now, in that case, your input power will be 3 into V into Is into cos phi. Fine. This is same as that of the synchronous motor only, because synchronous motor was also an AC motor. Now, in this, the power will transfer from the stator, then to the air gap, and then to the rotor. So ultimately, we want the power to be available at the shaft. So in that case, in this case, there is one difference between the synchronous motor and the induction motor. And what is the difference? The induction motor will rotate less than the synchronous speed. Fine. Whereas in the synchronous motor, the rotor was rotating at a synchronous speed, or you can say the magnetic field and the rotor was rotating at a synchronous speed. But this is not the case with the induction motor. Here in the induction motor, the rotor is rotating at a speed less than the synchronous speed. In this case, so it also means that there is a slip between your magnetic field, which is produced by the stator, and the rotor. Fine. So what is the slip? Slip will be equals to relative speed upon the synchronous speed, or you can say that is ns minus n upon ns. So we have written this slip in terms of the radians per second. So this one is the radians per second for a synchronous speed. This is a rotor speed that will be given as omega m. So now we know that how to go right, how to convert the revolutions per minute into radians per second. Now you know that ns will be equals to 120 f by p, that will be revolutions per minute, but we want in the revolutions per second. So in that case, you will have to divide by 60. Now when you divide at 120 f by p by 60, so what you are going to get, you will get 2 f by p. Fine. So just multiplied by 2 pi, and then you will get the 4 pi f upon p. That will be the radians per second. The number of poles are decided. Once you install the induction motor, once you design the induction motor, you cannot change it. Fine, you cannot change it. You can change the what you can say, the frequency of the supply. When you change the frequency of the supply, the synchronous speed is going to change, and accordingly your rotor speed is also going to change. So I think this is just a very important concept. So just now I had told you that any circuit can be drawn. We can draw the equivalent circuit for that system. So in our case, we are having the induction motor, and that too the three-phase induction motor. So this three-phase induction motor are broadly classified into three different parts. The first one is the stator. This is not the homogeneous part. Stator is different, then there is air gap, then the rotor is also different. Both these three things are made up of different materials, so we cannot say this as the homogeneous body. So in that case, the stator will be represented by, now this is the stator part, then there will be the air gap part, and this one will be the rotor part. So what we have represented, so stator will be represented by Rs into Xs. We can say that the stator means you will have to place the stator conductor, and the stator conductors are going to be made up of the copper winding only, and copper will be having the resistance and the reactance as well. So now the stator will be represented by by RS and the Xs, or any winding or any copper winding that can be represented by this components only. And you can see that this RS will be the frequency independent component, whereas Xs will be the frequency dependent component. Just take a note of it. Now there will be the reactant, that will be the magnetic reactor. So basically, we always ask people that what is the function of the reactive power. So the function of reactive power is to magnetize the air gap. So this induction motor is similar to a transformer. In transformer, we were having the iron path, fine, but in this case, we are having the air gap. So through this air gap, we will have to transfer the power from the stator to the rotor. So this air gap will be represented by magnetic reactance, because only the reactive power will be there. There is no real power. You don't require real power to magnetize the air gap. This is a thing you need to understand. So now there will be XR dash and the RR dash. As you know that there is a air gap, so we have taken the entire rotor part onto the stator side. Refer to the stator side if you have taken now. So there, then you will come to know that you will be having this dash part. So when you shift this XR dash and RR dash upon S, now why there is why the S appears in the RR term? Because as you know that there is a simplification, and you know that the EMF which get induced, the EMF which get induced in the rotor is not of the synchronous speed, is of the relative speed, because you know that induction motor is going to rotate at a speed less than the synchronous speed. So there will be a slip. So the EMF will be it will the EMF of the rotor will be S into E, and E will be the EMF at the standstill. You might have learned this, I think, in the lower classes. So that's why we have used this S. So keep it this only, S only. Now, this air gap, as you know that the reluctance of the air gap is very, very high. It is very, very high as compared to the iron path. So when the reluctance will be high, then you can say that then reluctance will be high. It means what? It means what? You can shift this part. You can shift this magnetizing part or this air gap part onto the this side, because that is required for the simplification purpose, nothing else. Or not this is the this is not the exact, this is the not the exact, this is the exact one, and this one is the approximate one. So either you can go for this circuit, or you can go for this circuit, fine. So now after that, so now you can see here voltage will be here, so you can easily find the rotor current, fine. The rotor current will be what? Because you can see here is will be here, and is will be the summation of, because some part will be going towards magnetizing the air gap, and some part will be entering into the rotor, fine. And why it is entering into the rotor? Because the EMF get induced in the rotor. So after having this approximate equivalent circuit, you can simply write IR dash. Now this V equivalent circuit are for per phase only. I'm not taking a three-phase part. I know, and initially I assumed that these three phases of the that induction motor are the balanced one. If you are taking that balanced one, then you will have to draw three equivalent circuit. That is for R phase, that is for Y phase, and for the B phase. So IR dash will be equals to, if you just just do the simple Ohm's law, you can say. Now you can see this RS and plus RR dash by S. These are the real part, and this one is the reactive part. So you just so there will be J term is going to appear. Fine. These are all the vector quantities, are not the scalar quantities, mind it. So now this RR dash by S, it means what? This is the air gap power, the power which enters into the rotor. Again, I am saying air gap power means what? The power which just enter into the circuit. Now, now the power which is entering into the circuit has to cater what? Has to cater what? The rotor copper loss and the mechanical power. Because ultimately we want the power at the shaft only, and that will be the mechanical power. But before that, your air gap power will be reduced by that rotor copper loss. So you can see that rotor copper loss will be equal to simple 3 IR square IR dash square into RR dash. Fine. Now for mechanical power means what? There will be a subtraction because the power which is entering the rotor circuit will reduced by some amount, and that reduction is done due to the copper loss. So PG minus PCU, just simple mathematics is there. Then this is the mechanical power which is available at the shaft, and this power is very much required to run the motor or to move the motor in the forward direction, and that is for the forward motoring. So T will be equals to Pm upon omega m. Fine, this will be Pm upon omega. Now just put the value. Now Pm upon omega m. Yes, and you just replace this omega m by this equation, or you can take the common here. So this one will be 1 minus omega upon omega ms. So after doing all the simplification, you are going to have this term. Now keep this term in mind because this is going to help you in the numerical problem. And now what you have to do, you just have to replace this IR dash by this equation we have already calculated. Now this is the IR square. So IR square means what? This will, the numerator will be V square only, and this is A plus JB form. So that will be A square plus B square. It means RS plus RR dash by S whole square, and this is XS plus XR dash whole square. So I think you are going to get this torque. This is the torque. This is the torque which is required for the forward motoring, and we have assumed that the rotor is below the synchronous speed, so there is no case that the power is going to reverse here. So now this is now if you want to have if you want to obtain the maximum torque, I mean, what is the maximum torque we can obtain? Now if you just refer the torque speed characteristics, I think it is here only. Now this is the torque speed characteristic. This is the stable region, or this is the unstable region. I have already talked to you about told you about this stable and the unstable part. So this is the maximum torque which we can have for our induction motor, but it all depends upon the load characteristics. I think we cannot achieve the torque speed characteristic, but we just want to understand means how much maximum torque my machine can can generate. So in that case, this torque just have some when so this torque will be obtained at a certain speed, so that will be having some rotor speed, and this one is the synchronous speed. So there will must be slip. So it means that you will have to calculate the slip at the maximum torque, and again you do some mathematics you can do. It was there in the lower classes, but after doing some mathematics, I think you are going to get this slip at the maximum torque. So after simplification, this is the maximum torque you can obtain. So I think that you need to learn this part, that is the torque part, or and this equivalent circuit is very important. If you want to if you want to solve in numerical, you need to learn this equivalent circuit. There is nothing magic behind this. Only thing that you will have to understand that the induction motor will be having three important parts: the stator part, the air gap part, and the rotor part. So this you will have to understand, not just T upon Tm. So I think this is the thing which we need to understand. And now we'll be taking some numerical. So now based on our understanding, we'll try to solve some numerical. So there is a numerical which is example 6.8. Now this is of 2.8 kilowatt, 400 volt, 50 hertz. There this squirrel cage induction motor is there, and this is delta connected. So I think this is a stator only, and the stator some parameters are given, that is RS will be equal to 2 ohm, RR dash will be equals to 5 ohm, XS will be XR dash will be equals to 5 ohm, and this one is the magnetizing reactance. So everything is given. So what we need to calculate, motor's speed is controlled by a stator voltage control. It means that if you want to control the speed of the induction motor, then you need to control the V. So as you can see from this equation only, this we have derived just now. That is T will be equal to 3 upon omega ms into V square upon R dash upon S upon RS plus RR dash upon S whole square plus XS plus XR dash up whole square. This is very simple. I think you require only 1 minute to remember this equation. So as you can see that V square is directly proportional to your torque. It means that if you just increase the voltage, then torque will be increase in that proportion. and you can have a speed control. So when driven by a fan load and it runs at a rated speed at the rated voltage, now you can see that the fan load means what? It depends upon, it is proportional to the square of the speed, fine. Or else you can say that it is 1 minus s ka whole square. That also can be done. I think in the first chapter only we have drawn some characteristics of the load, and that too a fan load. So fan load will be having some parabolic curve. So you might have, you might have remembered that thing. So anyways, no need to go for that. So I think first we calculate the synchronous speed, because this is very much required. First we'll try to calculate all the parameter depending upon the rated voltage, or you can say a rated things we can required. So this one will be ns will be equals to 120 f by p. 120 into, now here the frequency will be given as 50 upon 4. This one will be 1500 rpm. We don't require this in the rpm, because I think everything we are doing in the radians per second, and so that's why we need to convert this revolutions per minute into radians per second. So first we will convert this rpm into rps. Now how this will be converted? So this will be, you just have to divide this by 60. Only then it will get converted into that rps, and finally multiply it by 2 pi. So I think your answer will be done. So now then you calculate the slip, because the slip is very required, and you will know that the rotor will be having this much speed, and because you know that there will be a slip in the induction motor which was not there in the synchronous motor, so the slip will be easily calculated, fine. So now we just put all the parameter 3 upon, this is 50 pi, v square is also there, and it is delta connected. So in delta, the line voltage will be equals to the phase voltage. So no need to do any root 3 and all. That will be done only in the star case. This one will be 400 100 square into, now you will just RR dash will be 5. If you do all these things, so you'll get this thing, fine. Now for a fan load, that is torque is proportional to the speed square, I already mentioned, and I think if you're having any doubt, just refer the unit number one, you'll come to know this thing. So I think it can be written as k into, it is proportional means what? Something k will be there. K is a constant value, fine. If you can just write TL will be equals to what? TL is proportional to the n square, fine. Now you just write in terms of slip, because ultimately if you are changing the speed, it means what? You are changing the speed only, fine. And you just go to the slip part, no? This slip part will be, s will be equal to omega ms minus omega m upon omega ms. Omega m is a constant parameter unless you change the frequency. If you are changing the frequency, it is a if you then that synchronous speed will be a variable parameter. But if you are not changing the frequency, if you are not changing any pole, then the synchronous speed will be a constant parameter. So you just do the small mathematics. So you'll come to know that this will be the formula, or you can, it's not the formula for what is the formula for the fan type of load, not a generalized formula, I can say. So now, if you want to have the operating point, so operating point will be at T will be equal to TL. So you just, this is the electromagnetic torque which is developed by the induction motor, and this is the TL. This must be equal. Only then your motor will be operating at a steady state. Otherwise, not. So now I think you can easily calculate K value. Now TL will be equal to this. So now what is asked? Calculate the motor terminal voltage, current and torque at 1200 rpm. Fine. This is this you will have to calculate. So now initially it was, your induction motor was rotating at 1370 rpm. So now you will have to calculate this parameter at 1200 rpm. So what you do, just 1200 rpm, again you will have to change the slip. See, synchronous speed is constant, but in this case, you have to calculate the parameter, that is motor torque, current, and all for this, 1200 rpm. Speed has changed, so everything will be changed because slip has changed. No? Slip has changed, and the slip will be having more impact on the rotor. Slip will be having more impact on the rotor. So you need to calculate all these things only. And when the rotor current will be impacted, then it means that what? The torque is going to change. Fine. So we just S will be equals to what? 1500 minus 1200 upon 1500. That will be 0.2. So I think this will be calculated. So TL can be easily that is 36.9, and I think here T is also there. But you need to calculate what? Here you need to calculate the voltage. So I think in the formula only this is, yeah, this omega ms is a constant. V square, these parameters are constant, are also constant. So what is changed now? The slip has changed because 1200 rpm, so slip is calculated. So what is the slip? Slip will be 0.2. So just put 0.2, and I think you don't write now. Don't write this V as 400 because that was for the full load, or you can say a rated load. So this was the thing. Yeah, V square will be, because you need to find V only, na. So V will be calculated, and I think this IR dash. Yeah. Now, how to from where you got this equation? I think in just now I have told you about the IR dash, where it is from the equivalent circuit only, approximate equivalent circuit. Refer this one only. I think you'll get the things. So IR dash will be equals to, simple problem is there. IR dash will be equal to, I think so you will be getting some, the real part and the imaginary part. This is the real part and the imaginary part. I think you'll get, so Im dash will be equal to, Im will be what? Just B upon Jxm. What is Im? What is Im now? I think everyone is asking about the Im only. So I think Im is the current which is flowing through the air gap. So Im is this what, this V is the applied voltage across the air gap. So simply you can calculate, because we have assumed that our air gap has the reactive part. Yeah, because only reactive power will be required to magnetize the air gap. You don't require the real power. Can you just try it and just tell me whether it is possible or not? I don't think it is going to. It is possible. So I think IR dash is calculated. IM is, so IS can be easily calculated. So now this one is what your phase current. So root 3 will be your root 3, because you will be having the phasor, that is the angle also. So now this first part will be calculated. If you have any doubt, you can ask me always. So motor speed, current and torque for the terminal voltage of 300 volts. So now you see here, the voltage has changed. So when the voltage has changed, you see, obviously, so there will be a speed control now. So when there will be a speed control, so what is going to happen? There will be, when there will be a speed control, so I think everything will be changed only. So I think in this equation, everything will be same. Initially, we have changed in this, in the first part, we have written V as the unknown quantity. So now here slip will be at the unknown quantity, na? Slip will be the unknown quantity. So I think you need to solve again this. T will be equal to TL. So you'll get some, quadratic form. I think that's to the power 4. So for that you require the calculator. Initially that was V, now it is S, and the load torque is already in terms of the slip. So after doing all the simplification and all, so you're getting this thing, that is 41.4. And when you get the slip means what? Similarly, you can calculate the rotor speed, and this is, I think IS will be equals to Im plus IR dash, because this IR dash depends upon the slip. Yeah, why it is why it depends upon slip? Formula, just go to the formula. If you just think over it, no, so you can say that this is the stator current. The main stator current is entering, so there will be two parts. The first one is the air gap part, and second one is the rotor part. So IR dash will be equals to what? B upon RS plus RR dash upon S. So you can see here S term is there. This IM is constant. IM doesn't depends upon your rotor speed. Fine. Means how much is the reactive power required to magnetize the air gap is independent of the speed, is independent of the torque, is independent of the load, is independent of the teacher also. So so that will depend only upon the air gap reluctance and all. So this thing you will have to keep in mind. I think the problem is solved now. So you just line current again. This is the phase current value, and this is the line current. So this problem is very simple. So you can easily solve. So I think the next class will be doing slip power recovery. That way is a very important part. So I think till then, goodbye.